All right, new units, fundamental theorem of calculus. Last unit until or before the break. So test will be. Ooh, that's not a block day, so we may have to divide that test up. But the test is December, probably 10th and 11th. Maybe we can see how to split it up, if we need to split it up. Okay, the big thing for the fundamental theorem of calculus that we'll get to in a minute is this symbol right here. Because that symbol means two different things. And we've used both things, but we've kind of used them separately. We haven't really talked about like how they fit together. So this is from the last test. What is one thing that symbol means? Antiderivative. Means take the underivative, go backwards. Figure out what function has a derivative of, right, the Jeopardy game. Like, here's the answer, what was the question? Take an antiderivative. But do you remember what else that means? It means area. Yeah, the name of that thing is integral, but it means find the antiderivative or find the area. So the integral is asking for one of two things, but kind of both things. So like, how are those two things related to each other? And that's the fundamental theorem of calculus is, wait a minute, we use this symbol to say, do an underivative, go backwards. But we've also used this symbol to mean, like, what's the area under the curve? And so the fundamental theorem of calculus is, surprise, surprise, these things are equal to each other. The antiderivative tells you the area. And sometimes we even use it the other way. The area tells you the antiderivative. And maybe that seems weird because those are two separate, like completely separate ideas. Why does that work? That's why calculus is cool to those of us who understand it. Hopefully you get to the point where you appreciate it, that taking an underivative tells you the area under the curve. The parallel is taking a derivative. So antiderivative tells you area. What did the derivative tell you about the graph? What does the derivative tell you about the graph? Uh-oh. The slope. Like that's... I mean, that's all of calculus in one box right there, like conceptual-wise. Obviously, there's lots of rules to know, and there's applications of both of those things. But like big picture, the derivative tells you the slope of the curve. The antiderivative tells you the area underneath the curve. Like that is, if you had to summarize calculus in one statement, that would be it. The derivative tells you the slope. We know that. Antiderivative tells you the area. And all the concept questions on the AP test, like they all get back to this idea, like one of those two ideas. So we've done a lot of derivative tells you the slope stuff. Now we're going to kind of switch over and say that the antiderivative tells you the area. Okay, well now let's put some details on that and get some practice with it. If f is continuous and non-negative on the closed interval a to b, then the area of the region bounded by the graph of f, the x-axis, and a and b, so that's the shaded area here, between the x-axis and the curve, between a and b, is equal to the integral from a to b of f of x dx. So we kind of knew that already. That statement we knew, that means area under f from a to b. So that statement we know, and we used that statement on the last test, not because we could actually find the area, but we used estimates, those Riemann rectangles and trapezoids, to find the area. So this statement, maybe we're not super familiar with it, but we know that statement. That integral tells us the area under the curve. When the integral has boundaries, that's the a and b thing, a and b, it's called a definite integral. Without boundaries, it is called an indefinite integral. Because when you do an indefinite integral, you always get that plus c on the end. So your answer is indefinite. You don't know exactly what the answer is because I've got this plus c sticking on the end. We'll handle the definite thing in a minute, but indefinite is because of the plus c. The definite won't have a plus c, like we'll definitely get an answer. Okay, some vocab stuff here. The inside of the integral is called the integrand. So whatever's on the inside is the integrand. The boundaries are called the limits of integration, or just the limits or bounds. This gets maybe a little confusing because limits has another definition in calculus, right? Limit is x goes to 0 or whatever. So this is a little bit different, but the A and the B, those are the limits of integration, or the limits or the bounds. Rarely will I say limits of integration. I'll just use limits or bounds. And I try to use bounds to avoid the confusion with, limits. We have limit problems. This isn't a limit problem, but those are limits of integration. Okay, some properties. First one. This makes sense. If the boundaries are A to A, and think about what this means. You want the area under some graph from A to A. So you want the area under a curve from one point, but you don't really go anywhere. So it's this infinitely thin area. Well, that's no area at all. If the boundaries are the same, the area is 0. Number 2. If we switch the limits, or the bounds, or the limits of integration, it changes the sign. We'll frequently use this property when the lower bound is greater than the upper bound. We like the lower bound to be the lower number, and so if we want to switch them, we can. We just have to put a negative out front. This gets a little bit weird when we're talking about area, because you end up with negative area, which doesn't really make sense, but it's going to start to make sense in calculus. Because if we go from A to B, that's a positive area. But if we go from B to A, that's backwards. And almost always in math, if you're going backwards, you get a negative. And it's the same thing here. So if you switch the order around, it puts a negative out front. If K is a constant, you can slide the constant out front. You can take out the constant. I think we've used that. We just haven't really talked about that as a particular property. Okay, this next one looks confusing, but it's when we draw a picture, I think it'll make sense. If A, B, and C are constants, and C is in between A, draw a little picture here. So A and B, but C is in between there. Then, the integral from A to B, so that's the total area. Let's go from A to B, is equal to the area from A to C plus the area from C to B oh, well, yeah. The first part plus the second part equals the whole part. Well, from a picture standpoint, it's like, well, yeah. First area plus the second area equals the total area. So you can split the integral into pieces by splitting up the boundaries. AP likes this one on FRQs. They do like to use that property. Number 5. You can split the integral into pieces by splitting up the integrand, just as you did with derivatives. We've done this already. You didn't even realize we were using a property on that test. when you had to take the integral or the antiderivative of two different things? You just took the antiderivative of the first one and the antiderivative of the second one. It's like, this property makes sense. You've done that before. This last one, the antiderivative from a to b of k is a constant. So think about what this means. If k is a constant, so I've got y equals k here. And I want the area under that curve from a to b that's just a rectangle, so the area of that curve, base is b minus a, the height is k, so the area under that curve is just a rectangle. This is useful to remember when the integrand is just a constant, because you're finding the area under a straight line, so it's just a rectangle. So those are some of the properties that we'll use. I feel like most of them make sense, so most of them you don't really have to memorize those properties. So you don't go home and put each of those properties on a note card and remind yourself of them. I think most of them make sense. So we'll just use them as needed. All right, evaluate the integral by graphing the function between the two boundaries and using a geometric area formula. Okay, so remember that integral means two things. It means antiderivative. We'll do a bunch of those. You did a bunch of those already. But it also means area. So these two problems, we're not really going to take an antiderivative. We're going to find the area using geometry. So let's see. Absolute value of 2 plus x. What does that look like? Do you remember what the absolute value looks like? Forget about the plus 2 thing. What's the absolute value look like? The v. And I don't like 2 plus x. I would write that as x plus 2. So do you remember your transformation rules? Like, what is x plus 2? What's the plus 2 do to the graph? It shifts it left 2. So we're going to take that v that we like and shift it to the left 2 spots. We're going from -4 to 4, so 3, 4. And we got to go up 1, over 1 the whole time. 2, 3, 4. So there's my graph of y equals this absolute value of x plus 2. The area under the curve, or under the, is sort of two, not sort of, it is two different triangles. And so all I have to do is find the area of the triangles. So I'm not really doing an antiderivative. I'm just knowing that that symbol means find the area. So let's see, area of a triangle is 1/2 base times height. So let's see, this is 2 times 2 is 4. Divided by 2 is 2. So that area is 2. This area, let's see, from -2 over to 4 is 6. Which means the height has to be 6. So 6 times 6 is 36. Remember your geometry, that'd make a whole square, but we want half of the square. So 18. So the answer is 20. Not because I really did any calculus, but because I know geometry. calculus I did was just understanding that this means the area from -4 to 4 underneath that graph. Number 2. I'm guessing most of us probably don't know what that graph looks like. So not great initially. They like to use, AP likes to use this equation though, and because it converts easily. Do you see what I could, well, it's already solved for y. What could I do to get rid of the square root? Square both sides. So y squared equals 25 minus x squared. And then if I move the x squared over, x squared plus y squared equals 25. And hopefully, maybe, you remember what that is from either Algebra 2 or Pre-Cal. Recognize that shape, that formula? Nah, you're thinking maybe derivative, but like just geometry, like what graph what's the graph of that look like? Nope. X squared plus y squared equals 25. A circle. That's a circle. A circle with center at 0, 0. What's the radius of that circle? Just coming back to you now? 5. Now, let's be careful when we graph this thing. We glossed over something here when we squared both sides, or when we take the square root going the other way. This is only the positive side, so it's only the top half of the circle. So -5 to 5, which is what it asks for in terms of the limits or the boundaries. So the area it wants is the area of that semicircle. So let's see, that would be half. Correct. So the area of a semicircle, that would be 1/2 pi times 5 squared. And you could leave that as an answer like that, right? Safe stop. So we do expect you to recognize that that is a circle. Right? It doesn't look like the circle you used in Pre-Cal and Algebra 2, but with a little bit of rearranging, then it looks like a circle. So that is definitely something you'd be familiar with. You will see that. All right, so the graph of f composed of 5 line segments is shown above. Let's find all of these. Okay, remember that symbol means antiderivative, but I don't really want to do antiderivatives. I'd much rather use area. Area under the curve. Okay, so the area under the curve from 0 to 3. 0 to 3, 0 to 3. Okay, this looks unlike stuff we've done before. Why is that weird? Do you see what makes that different? You're on the right. Well, it sort of looks, yeah, it's not a perfect V, so it's not absolute value. Right, the area under the curve, usually our curves are above the x-axis, and we take the area down to the x-axis. Now our area is actually under the x-axis, and we're finding area that's under the x-axis. You want to guess what that does to our answer? Makes it negative. Anytime you switch something in math, something gets negative. So this area, let's see, it's the area of a triangle. 3 times 2 divided by 2 is 3. So let's be careful. That area is 3. Show my work here. 1/2 base times height. Base is 3, height is 2. So the area is 3. But the integral, because it's under the graph, is negative. Area under the x-axis is I guess I should say a negative integral. The area is still positive, but the integral is negative because we're under the x-axis. That should probably not be problem 1. All right, the area from -5 to 0. From -5 to 0. It's a trapezoid, but Barrett, where'd you get 4 from? Perfect. 4. Count the squares. Right? Don't overcomplicate things with formulas. When there's 3 squares in the middle, there's a half on each end. So 3 plus a half is 4. Or maybe from left to right, a half plus 3 plus a half is 4. Right, so it's geometry, but it's also just count the squares. All right, from -6 to -4. -6 to -4. Color coding my answers here. Why 0? Right, so from -6 to -5, that answer is -1/2. But then from -5 to -4, that answer is a +1/2. So the total is 0. So that one, again, the negative area is what throws people off sometimes. So that the total green area is 1, sure, but half of it's negative, half of it's positive. So combined, it makes 0. So part D, you just go all the way from -6 to 5. So I think I would just kind of count the squares or add the area as we go for part D. So let's see, from -6 to -5, and then from -5 to 0, and then from 0 to 3, and then from 3 to 5. So like I'm breaking it up. I'm using one of those properties that we talked about earlier that we don't really worry about the name of it. I'm just going to add up the areas as I go. You know what? So let's pick on people. Pick on people who are in second period. Okay. Give everybody a little bit of a heads up so they can see what's coming. Audrey, how about from -6 to -5? What's that integral equal to? It's -1/2. Good. That one's -1/2. So it's a triangle that has an area of 1/2, but it's below, so it's negative. Barrett, how about the area from -5 to 0? 4. That's 4. That's the one that you saw earlier. In fact, that was question B. Was the area from -5 to 0? Isabel, how about the integral from 0 to 3? Good. And I was careful how I worded that. The area, you might say, is 3, but the integral is -3 because we have to put the correct sign on there. And then Harper, the only one we haven't done yet, so puts you on the spot. What's that integral from 3 to 5? 1. The area is 1. The area is 1, but what's the integral? -1. And why is it negative? Because it's below the axis. And I guess as a safe stop, we could just leave it like that and call it a day. But that's not too hard to add up. Oh, especially when 4 minus 3 minus 1 goes away. Use the safe stops. Most of you did on the Riemann, back on that test, but there was a few people who didn't safe stop and then made a mistake, and so they lost a point because what they put on their test was wrong, even though it was just an algebra thing. And so it was a completely avoidable deduction because they could have left it as a safe stop. Okay, part E, 5 to negative 6. What is weird about this thing? It's backwards. I don't like backwards. So I would like to go from negative 6 to 5. I would like to make that swap. What price do I pay if I want to swap the limits? Make it negative. Okay, now that answer that's actually the answer to part D. That is what we just found. So negative 1/2 would be a positive 1/2. Part F. What does absolute value do to a graph, or do to a number, do to a value? Makes it positive. So that means all areas are positive now. Nothing is below the axis. So I'm still going to work my way from left to right, add up all the pieces, but there's no negative pieces anymore. So I'm still going from negative 6 to 5, negative 5 to 0, 0 to 3, and 3 to 5. Once you get the hang of this, you're not going to label everything like this. You're just going to add them up in your head and write the answer down, and that's okay. But for now, let's take it slow and see what we got as we move across. Graham, Ryan, Evan, and Leah. So Graham, how about that first one, that first piece, from negative 6 to negative 5. Oops, that should be a negative there. From negative 6 to negative 5.
It's just negative 1/2. Or no, it would be positive 1/2.
Why is it positive?
Absolute value.
Because of the absolute value. So it was negative 1/2 because it's below, but the absolute value makes everything positive, so it's positive. Ryan, how about negative 5 to 0? 4. So the absolute value didn't really do much to that one. It was already positive. Evan, how about 0 to 3?
3.
Just 3. Why isn't it negative? Because the absolute value. And then Leah, how about 3 to 5? 1. Same thing. It was below, but absolute value made it positive. I'm out of space, so I will safe stop that. But 8.5 would be the answer. Ryan, you okay? Were you looking at from negative 5 to 0? It is a trapezoid, but even easier than seeing it as a trapezoid, just count the squares. The area is 1 square, 2 squares, 3 squares, half a square there, half a square there, so that makes 4. You can use the trapezoid formula and you'll get 4, but for something like that, just count the squares. Oh, look carefully at G. It's supposed to be an easy answer if you look very carefully at G. Look at all the pieces there. And it's a trick question, but Lexi's good for a trick question.
Is it 0 because it's 4 to 4?
Perfect. The area from 4 to 4, there's not any area from 4 to 4, so that answer is 0. Because those limits are the same. We didn't go anywhere. So we like that question when it comes up. All right. Part H has a 4 front, but I can just move the 4 out to the front. And then whatever the area is from 0 to 5, I'll multiply it by 4. So 0 to 5, there's 2 pieces in there, but I bet Braden can combine all that by now. We've labeled things. What's the integral from 0 to 5, Braden? Good. I'll write exactly what you said. -3 plus -1. Because that's how you would see it. You'd see the 2 triangles, -3 and -1. And then that would be a safe stop, so you could just stop there and call it a day. -16. All right, the last one. We're getting a little more complicated here. I'm going to split this up into 2 pieces because I don't want to do 3 times the graph plus 2. I guess that would be one way to do it, is to like redo the graph, but I don't really want to do that. Instead, let's split it up like this. We can take out the 3, we can separate the 2, and now we're still looking at just our original function. We don't have to do anything to the function. It's like we just found that area. That's the same thing I asked Braden. That area from 0 to 5 was -4. Okay, this one's not on our graph, the second part here, but I know what the graph of y equals 2 looks like, and I want the area under that from 0 to 5. So the area under 2 from 0 to 5, I can sketch it if you need me to. X, y, there's y equals 2. So, Hector, what's the area under the graph of y equals 2 from 0 to 5? 10. It's just a rectangle. And again, you could safe stop that, box that up and call it good. Or add them up and get -2. Okay, so far everything's been area, just area. Here comes the big fundamental theorem of calculus. The big concept that Isaac Newton used. Go ahead, Emma, what's up?
So how did you get the 10?
The 10?
Yeah.
Hector, how'd you get the 10? You said 10. Where'd that come from?
The base, which is 0 to 5, and then height, the 2.
Does that make sense? He just did a rectangle. And he knows that a rectangle is base times height, not base plus height. I shouldn't say that in that other class. That person will feel bad. Okay, this is the big concept that Newton used to do all sorts of stuff. The method of fluence. Like, we don't need all the history there. But the big thing is, if we take an antiderivative, so if we antiderivative the derivative of f, antiderivative, that's what that symbol means. F prime, that's a derivative. So we get back to the original. This was on like 3 worksheets on the last unit, and it was also kind of a gimme question on the test, although there was one person that missed it. You know the question I'm talking about? It was the antiderivative of f prime is equal to f. Don't forget the plus c. That question. It's supposed to be a freebie because it leads into what we're doing now. Still true. The antiderivative of the derivative gets me back to the original. What's new is we plug in the top minus plug in the bottom. So you take an antiderivative and then, running out of space, plug in the top limit, plug in the bottom limit. plug in the top minus plug in the bottom. Take an antiderivative, plug in the top minus plug in the bottom. That's what we're going to be doing for the next, well, in some ways, couple days, but in some ways, rest of the year. Take an antiderivative, plug in the top, minus plug in the bottom. Okay, so number 5. Well, first let's remind ourselves that this means area under that curve from 0 to 1. So we're looking for the area under 2x minus 1 squared from 0 to 1. But I don't know what that graph looks like. And even if I did, I mean, it's a parabola. There's not a formula for the area under a parabola, at least one that we know. So yes, we're going to find that area, but I can't use the geometry stuff like we did on the last page, like triangles and circles and trapezoids and rectangles. Like, that's nice, but now we got a parabola. So instead of doing area, we're going to use the antiderivative. So let's square this out. 4x squared minus 4x plus 1. All right, algebra first. Then I can antiderivative each of those pieces. This is what the last test was. So one piece per person. Elizabeth, what's the antiderivative of 4x squared?
4x to the third divided by 3.
Good. Emma, the antiderivative of minus 4x?
Oh, wait, where are we? Oh,
The antiderivative of just that guy.
2x squared.
Look at her doing math in her head. Increase the power by 1, divide by 2, you get back to 2. And Cody, the antiderivative of 1? X. Okay, on the last test, you would have stopped there and put plus C. But now we've got limits. In fact, I left them off. Shouldn't have. We're going from 0 to 1. We haven't used the 0 to 1 yet, so I need to indicate that I'm going to use 0 and 1. Here's how we do that. We put a closed bracket at the end, even though there's no open bracket, so that feels a little bit weird. But a closed bracket with the 0 and the 1. So when it was on the left, we hadn't used it yet. We've done the antiderivative. We still haven't used it yet, but now we're saying we're going to plug in the 1 minus plug in the 0. Plug in the top minus plug in the bottom. So let's plug in 1. I'm going to overkill this because it's the first one. So there's plug in 1. Minus, we'll plug in 0. You can probably see what's going to happen when we plug in 0. But that doesn't always happen. Like, what am I alluding to? What am I going to get if I plug in 0 everywhere? I'm going to get 0. Just be careful. That's not always the case, because you might have a cosine of 0 in there. You could have a constant in there. So be careful. Don't just assume that you can ignore if the 0 is at the bottom. So I'll show my work here. Once you do a few of these, you're not going to show this, and that's okay. Plug in the top minus plug in the bottom, and that's a safe stop. So lots of safe stops on these. You do have to plug it in, right? You can't leave it like at this line. That's not a safe stop, because you can't put that in your calculator. There's no way to put that in the calculator. So you got to do the substitution, but once you do the substitution, you can stop there. Plug in the top minus plug in the bottom. And then that tells you, I'm going to find it because I'm curious. 4/3 minus 2 plus 1. Oh, I've got to do fractions in my head. So what is that? 4/3 minus 1 would be 1/3. So what I just found was the area underneath the parabola, without using geometry, but using calculus instead. All right, number 6. Oh, that's the one some of us missed on the test. Right? Not worried about the 1 and the 4 yet. Let's worry about doing the antiderivative. Laura, how do I think of the square root of u?
U to the negative 1/2. This on the bottom.
Yep, so that's u to the negative 1/2 if I want to put it in the top. Again, there's no product rule for antiderivative, so I need to distribute that. Oh, I should show all of the work here. So that's u to the 1/2 minus 2u to the negative 1/2. I still need to show that integral symbol there because I haven't used the integral symbol yet. Some of you drop all the symbols and I can't follow what you're doing. So show me what you're doing. Yeah, it's sort of like if you were working on... never mind, that wouldn't help. Okay, so now I need to take the antiderivative of those. Oh, it's a little bit harder. But hey, we just tested on this, so we can handle this. I think. Helen, what's the antiderivative of u to the 1/2?
U to the 2/3 over 2/3. Or 3 over 2, sorry.
Yeah.
U to the 3 over 2 times 2 over 3.
There you go. U to the 3/2 times 2/3. Yes, because that would get us back to u to the 1/2 if we took a derivative. Maddie, how about the antiderivative of 2u to the negative 1/2?
4 U to the 1/2.
Increase the power by 1. And when we divide by 1/2, yeah, that would get us to 4. With an indefinite integral, when we didn't have limits, we would just put plus c and be done. That's what the last test was. Now we have limits. So we're going to plug in the top minus plug in the bottom. Plug in the top minus plug in the bottom. So when I plug in 4, 2/3, 4 to the 3/2, minus 4 times 4 to the 1/2, minus, now let's plug in the bottom, 2/3, 1 to the 3/2, minus 4 times 1 to the 1/2. That's a safe stop. In fact, that's why we like safe stops, right? Because that's ugly, but I don't want to mess with it. Now, on a multiple choice test, I'm out of room here, but I think we can afford to take some from number 8 here. Okay, safe stop. We're good there, but multiple choice, we're going to clean that up. So let's remember how to do the root and power thing. So I need the square root of 4. That's 2. 2 cubed is 8. Times 2/3 would be 16/3. Is that too much in my head all at once there? Two-thirds of 4 to the 3/2 is 16/3. Next one's a little bit easier. 4 times the square root of 4, that'd be 8. So minus 8. Minus, the ones are nice. 2/3 minus 4. That's a safe stop, but if you were doing a safe stop, you'd have stopped at this step before that. So let's keep going. 16/3 minus 2/3. If I combine those, I get 14/3. And then negative 8 plus 4 is minus 4. So 14/3 minus 12/3 is 2/3. That would be the multiple choice answer. On your own, obviously you're going to pick the safe stop so you don't have to mess up anything, but we like throwing multiple choice at you to make sure that your algebra still works. And that's also why sometimes I do the partial credit even on multiple choice questions, because if I can see all of that work, it feels a little extra punitive to take off 5 points if the only thing you messed up was some fraction stuff at the end. Okay, so now we're just practicing. Like, we know all the rules now. Take an antiderivative, plug in the top, minus plug in the bottom. Selah? Trig. Yeah. Do you remember who has a derivative of secant squared? The derivative of secant is secant tangent. So it's not secant tangent. You need to think backwards. There's a function whose derivative is secant squared. Somebody help her out. Tangent. So tangent of x. And again, on the last test, we'd have put plus c and being done. But we don't have that option anymore. Now we've got to plug in pi over 6 and negative pi over 6. We're like one line away from you really liking what I'm going to tell you. So tangent of pi over 6 minus tangent of negative pi over 6. Keep my color coding here if we need it. Plug in the top minus plug in the bottom. Okay. The rules on safe stop is you're done with calculus and it's calculator ready. Tangent of pi minus tangent of negative pi over 6. Excuse me, tangent of pi over 6 minus tangent of negative pi over 6. Is there any calculus in that line? If I had a scientific calculator or a graphing calculator, could I plug that in and get an answer? That's a safe stop. So, don't tell your pre-cal teachers. I mean, they already know, so you can tell them, but you can get away with, I can't believe I'm about to say what I'm about to say. Alec, what I'm about to say? You can get away with not knowing your unit circle. For a free response question, you can get away with not knowing your unit circle. That's true. Now, on a multiple choice test, we're going to keep making you know the unit circle, and, oh, I'm tempted to pull a popsicle stick. Somebody like, oh gosh, please no. So I won't. What's the tangent of pi over 6, though? Root 3 over 3. And the tangent of negative pi over 6, I might have to draw that one to think about it. Negative root 3 over 3. It's in the fourth quadrant, so it's negative. So negative root 3 over 3. I guess if we made it that far, that would be 2 root 3 over 3. I should have stopped recording so I wouldn't even put myself on tape saying you can get away without knowing your unit circle. That's not what a math teacher should be saying. Number 8. Secant squared over 1 plus tangent squared. It's like, wait a minute, that was on the test too. Do you remember what 1 plus tangent squared is equal to? That one is equal to secant squared. So originally this one looks terrible because I got secants and tangents and squareds and pluses. But now I've got secant squared over secant squared. Thank you, sir. Ryder, this is for you.
Thank you.
Secant squared over secant squared? Should pull a popsicle stick for that one, right? That would be 1. Now the next one, I guess, it's supposed to be easy, but sometimes it throws people off. So, Avery, I'm not saying it's easy. If you understand it, it's not bad. What's the antiderivative of 1?
X.
Almost. I'm not in X land, I'm in theta land.
Theta.
So theta. Now, it's unlikely you would get that problem wrong if you put X, because then right away you'd plug in pi over 4 and 0 and you'd be fine. But officially we should put a theta there. So plug in the top, minus plug in the bottom, and we get pi over 4. Let's skip number 9. It's trig, but it's not bad. Let's do number 10 just because of the algebra. Square root of 2 over x. I'm going to rewrite that as the square root of 2 over the square root of x. And I don't really want to mess with the square root of 2. So I can take the square root of 2 out front. sort of like prep work to make my antiderivative easier. And then we've seen this before. Zach, if there's a square root in the denominator, how could I write that as something with just a power? Yes. That will make life much easier. More than that, I can't take an antiderivative of something in the bottom. You have to make it into a power. Now you can use the power rule.
How come you just move the square root to the side?
That was one of those properties that if you're multiplying by a constant, it can slide out front and you don't have to worry about it. So any number that's on there, 3, 5, -7, you can slide it out front and then you don't have to worry about the antiderivative of it. Speaking of antiderivatives, Tristan, how about the antiderivative of x to the -1/2?
So then like 2x to the -3/2.
Wait, increase the power by 1. You're starting at -1/2.
Just normal.
So normal 1/2. And then divide by the new power. Well, divide by 1/2, which is the same thing as multiplying by 2. Maybe I'll show the. So I've got 2 root 2 x to the 1/2 from 1 to 8. So 2 root 2, and I can put that 2 root 2 out front.
Just a reminder, teachers, that was the ADA bell. Please take ADA attendance at this time. Thank you.
Plug in the top minus plug in the bottom. Plug in the top minus plug in the bottom. That's a safe stop. But on multiple choice, how do I simplify the square root of 8? You remember what that is? 2 root 2. Square root of 1 is just 1. And then here's why I picked this problem, because algebra. If I distribute 2 root 2 times 2 root 2, Claire, what's 2 root 2 times 2 root 2? 8. 2 times 2 is 4. Root 2 times root 2 is 2. All that to get 8. And then 2 root 2 times 1 is just 2 root 2. There's my multiple choice answer. Yeah. Calculus is easy, algebra's hard, right? That's why I picked that problem. Okay, big picture. Take an antiderivative, plug in the top minus plug in the bottom, or there's the geometry problems where it's just a geometry formula. So that was like long notes, but it's really not